officially start the recording. So welcome back. Thanks for being here. Homework questions. Let's open with that. So your next homework is due Monday. How's that going?
Submitted.
Submitted. Excellent.
Yes.
First half is done. That's great. Any questions that I can help with? Those of you who are still working on it?
I would recommend not waiting to the last minute.
Oh yeah, I would always recommend that. I would always recommend that as a strategy, but make sure you are properly fueled before you try to do your homework. That's another good one.
Which is why there's candy here.
Yeah, exactly. Proper fuel, for sure. Definitely not going to make you hungry again in about 20 minutes. Definitely not. Nope. Yeah, I really wish I would have figured out that whole, like, carbohydrates make you hungry thing much earlier, because I did cross country and track in high school, and I felt like I was hungry at, like, every minute of the day. But I look back at what I was eating, it's like, oh, pasta, bagels, oh, no wonder.
In, out, gone. Next.
Yep, pretzels, really healthy stuff like that. Anywho, so homework questions are okay for now. Let's see. Yeah, after that'll be a formative assessment, then another homework, and I'll let you know when that stuff is ready. I think we have the rest of example 4B to do today, and that'll be it. So we might get done a little early, maybe. We'll see. Yay! Yeah,
Ooh.
maybe. Yes, well, I need to leave campus right after class, so I'm sure that will work out just fine for all of us if we do get done a few minutes early.
Is it a happy reason, I hope?
Yeah, so my son is in a bowling league on Saturday mornings.
Huh?
And we are taking him today to get fitted for his own bowling ball.
That's exciting.
Yes, because apparently that is really important to have a bowling ball that fits properly for your little fingers and isn't too heavy. Go figure.
Yeah.
So,
very good.
Yep. My son is not going to be the star athlete. He's in the chess club. He goes bowling.
Chess club is great.
He
and
went
also you get less concussions usually playing chess.
Yep. I am totally fine. I like how you said less concussions and not none.
Well, say none. No, let's say less.
Well, those chess pieces can be heavy, right? You get an opponent that doesn't like your style of
Boom.
play. Yeah. Yes. Well, he does that at his elementary school, so I'm guessing their chess pieces are deliberately designed to not hurt people, because children hurt people. Their little amygdalas make them crazy. But anywho, let's see here. This example we were working our way through. This is data set that I simulated based on real data. The real story is older adults who are being measured. This is a cross-sectional part of a longitudinal study. We have age as a predictor. Grip strength, which is pounds per square inch, supposed to be an indicator of physical function. Binary sex, and then dementia status. People who are never going to get it during the study, people who have it, or who are going to get it but didn't when they started, and then people who already have it are the three categories here. And last time we'd walked through the coding process to turn these into predictors. So remind me again why I'm doing this. We've got the how down, but I don't want to forget the why. We're centering. Why are we centering?
So the graph will be a better y-intercept.
A better y-intercept. So how does centering affect the y-intercept? Yeah. It does? Yes, it does. The slope doesn't change yet. Next week it does. Next week it does. Yes, for moderation, exactly. So yes, the intercept, the fixed intercept is the expected outcome when your predictors are 0. So if I did not center, I would be predicting cognition in newborn babies who can't squeeze anything. Well, that part works, but the cognition part is maybe a little weird because I'm using older adults to predict information about newborns, and that's a little weird. Now, it doesn't really matter in these models per se, like it's not going to change anything. If I estimate my model and get a weird intercept, my R-square is the same. In this model, my slopes are the same. The predictions that the model makes are the same. So at this point, it only concerns the intercept. But where we're headed next week is moderation analysis that involve interaction terms. And what's going to happen is that two variables that interact, their slopes become conditional on the 0 of the other one. So then 0 means, then it matters. So, yep, that's next week, though, not today. And what am I doing here? Why am I doing this?
You're creating a reference group.
Well, I'm creating
Or a
two new
reference.
variables out of my categorical predictor.
Right.
So why am I doing that? We'll look at the R code 2 here. Could I put dem group 1, 2, 3 in the model as is as a predictor? Would that make any sense?
No, you couldn't, because they're not,
I mean, it will let me, but is it a good idea is the question. And you say no?
it's not a good idea.
It's not a good idea. Why not?
Well, they're separate groups,
They're separate.
and so they can't all be, I guess, active at the same time. I don't know.
Well, it's not allowing you to make a comparison because we're using that reference group.
So if I just put dem group in the model, it's scored 1, 2, 3.
Uh-huh.
Are these numbers? No, they're
No.
not numbers. That's the problem. These are labels.
Mhm.
So if I put dem group in as a predictor and I pretend that it is a quantitative predictor and that these are numbers, then I'm saying that the difference between none and future in terms of their predicted cognition has to be the same as the difference between future or current, future, and current. And so I'm essentially assuming that the two differences are the same. And that's an empirical question. So it is not a good idea, I would say. The software will let you. So what we are doing is turning it into two quantitative variables. They're technically binary, but they're being treated as quantitative in the model. So by setting the 0 for the first one, what am I doing?
The reference.
That's my reference. Yep. Same idea as centering, but it's called recoding when it's categorical predictors. But you're making 0 mean something is the key idea. And so then the second one, the second group gets a 1 for the first variable, and the third group gets a 1 for the last variable. So then the names of these I chose to indicate that NF means none versus future is the contrast, and NC means none versus current. And now that is relevant because we started looking at descriptive statistics. So why is dementia group not in this table? Because it's not a number. Like this summarize and describe, these are used for binary or quantitative variables only. If you want to get category frequencies and proportions, that is tabulate or in Stata, or table, prop table turns those into proportions in R. And by the way, this means include a category for missing if there are, so you can see how much missing data you have as well. That is sort of implied in this table because they list the n for each, and so if you have missing cases, then you would have a different n for that variable, and that's how you would know.
Interesting.
It's useful.
It is.
Yeah. Okay, any questions so far? We started looking at correlations.
Mhm.
So what we are doing here is trying to understand how each variable relates to each other bivariately, meaning just two at a time, because that should inform what we might expect in our model when everything is combined. So negative correlations in the table, what do those mean? What does a negative correlation mean as a general rule?
Decreasing.
As x goes up, y goes down. Yeah, it's like the disco rule. Negative correlation is disco. And positive correlation then, as x goes up, y goes up. Maybe a different move, but less disco. Now, what's not in my table in terms of the variables in my story?
Your categories.
Yeah, I got cognition as my outcome, or cognitin, as it is labeled up here with the tilde. I have age and grip strength and gender. I don't have anything for dementia in here. Could I have put those two new dummy codes in this table?
Yes.
Could have. Is it a good idea?
No.
No. So if we look at like each of these by themselves, if dem NC is not in the model, dem NF does not mean what I think it does. Look at what the 0s and 1 pattern is here. What does this variable mean when it's in isolation?
None and current are the same.
Yeah, none and current lumped together versus future is what that would be. So the correlation between cognition and that would not tell me anything about what this variable is going to do in a model. Likewise, if I just stuck dem NC in there, this is none and future lumped together versus current. So they only have meaning in the context of both of them working together. That's why they can't go into the table. Does that mean that I can't get a bivariate relationship between dementia group and cognition? Am I just done? No, never done. Never done. What can I do instead to figure out how dementia group relates to cognition?
Can't you just make a linear model?
Make a model, yeah. We know how to do that. We've got the technology. So then if I make a model, I can get an R square out of that model, right?
Mm-hmm.
Can I take the square root of that R square and turn it into an R? Yeah, I can. And then I kind of have a correlation. Then I have something that is comparable in interpretation, just built through different mechanisms. So in R, there is a default core function in base R. It doesn't give you p-values in an organized way. So I found one that does, and this is a package called, HMIS. I think that stands for miscellaneous. It wants you to turn your data set into a matrix to use it, and then you have to list out the variables you want as well as the kind of correlation that you want. So by the way, Pearson is one kind. There's a whole bunch of kinds of correlation out there, though. So when you report these things, be specific. These are Pearson correlations specifically. That's kind of the default, but it's not necessarily the right answer for different kinds of data. So then R packages this much more succinctly, and the p-values are in a separate matrix over here. Okay, so then, I want to make sure that the bivariate relationships that I have described are accurate. So in a correlation, what is the assumption about how age relates to cognition? What kind of relationship pattern does a correlation imply? Yeah, and is it level off at all? Or does it just keep going?
Just keep going down.
Yeah, correlations are linear relationships. Do you think that age relates to cognition linearly?
Depends on your span of age.
Yeah, it depends, but I think it's a question, like whether there's
Is
something
there?
else there. Likewise, grip strength and cognition. Is that relationship going to be linear? Not necessarily. What about the relationship between binary gender and cognition? Is that relationship going to be linear?
Mm-hmm.
It has to be, because there's only a 0 and a 1. So there's only one interval, it has to be linear. In this data set, and I will remind you that the original study was conducted in the 1980s. Gender was binary and no one thought to ask otherwise at that point. So it's a dated example in that regard. So then let's check those assumptions. So we haven't really talked about the assumptions underlying the models that we're learning this semester. That's going to be in the last unit, because that is my deliberate sales pitch to get you to come to future courses to solve the problems if they're violated. Because it's no good, like, oh, check your assumptions. Well, what if they're violated? Oh, I guess I'm done, sorry. That's not going to work. Sorry, NIH, I know you gave me $4 million to do this study, but my assumptions are violated, so I just can't. No, that's dissatisfying. One of the assumptions that people say about linear regression, probably because of the name linear regression, is that the relationships have to be linear. Nope, that's not an assumption. The assumption is that the model is right. So if you put in a linear relationship, you are assuming that it's linear. If you put in a quadratic relationship, you're assuming that it's quadratic. You're assuming the model is right with respect to the fixed effects. That's always the case. The rest of the assumptions have to do with E. And I will tell you briefly, E is supposed to be normally distributed. E is supposed to have constant variance across predictors and people. And it is supposed to, what's the one I'm missing? Oh, the big one, be independent. We are assuming that this is a simple random sample independent. But if we have older adults who are nested in nursing homes or something like that, then E is not sufficient, and then you need additional coursework. Or the YouTube. Additional models is the key idea. So I'm fitting a quadratic effect of age to see if that improves the relationship between age and cognition. So is this still a bivariate analysis, do you think?
Well,
Bivariate means two variables at a time. To me, it kind of is, because you're still talking about age and cognition. Like, it's just that the way they're
Yeah, different
relating
number of
is a more
slopes.
complex function. Yeah, like, I think of this as bivariate because this is the same variable. But you can, that's a reasonable thing to disagree about. So now we know how to do this, right? So first stop, model our f-test, significant, r-square, 3% of the variance, woohoo! Age ain't nothing but a number, that's what that means. Now the question, do we need the quadratic slope? Where do I look to make that decision?
Can you compare the r² values?
I can. But I have a more direct answer in front of me. Let's put it this way. We had r² before was this, 0.0291. Now it's 0296. So it changed in the 4th decimal place. Doesn't look like it matters, right? So I can just look at these numbers and go, they don't look different. But reviewer 3 is not going to be happy with that explanation. How can I test whether this model is better than just allowing a linear relationship? I will give you a hint. The answer is on the screen.
I was gonna say, isn't that like how we compared like two different ones that weren't already compared earlier?
So this is the part that would be from the correlation, right? Age is a linear slope. Correlations are linear relations. So here's the new component, the quadratic slope. That's the difference. So if the r² increases, it has to be because of this variable. So then the p-value for this is 0.58. So is this significant or not? Decidedly not. In other words, if the true quadratic age slope were 0 in the population, we would find one this different than 0 58% of the time. So it's well within expected sampling fluctuation around 0. It's nothing to write home about. So this p-value directly tells me that the change in the r² that resulted from adding this quadratic slope is not significant because the quadratic slope is not significant. 1-to-1 correspondence when you only add one thing. So I would argue we don't need it. There are more higher order terms. You can do age to the 3rd power or the 4th power, but that's a little crazy. There's not many cases in which that would be a reasonable expectation. Corresponding R code is down here, so I'm going to alternate outputs across the two programs. So let's talk about that model. 24 is the expected cognition for what kind of person?
Center at
85, yeah. So an 85-year-old. The slope that's for linear age is also at 85. It is the instantaneous rate of change. So as age goes up, cognition goes down. What, in terms of just the signs of the coefficients, what is the quadratic slope doing? What kind of function? Yeah, this is like a hand question. Is it speeding it up or slowing it down?
It's actually slowing it down.
Yeah, see, if you look at the sign, it's like, well, it's positive. It's got to be speeding something up. But you have to know the sign of the linear. In this case, because the linear is negative, the quadratic is making it less negative, which is slowing it down, even though the quadratic slope is positive. In general, as a concept, if they're in opposite signs, it's a slowdown function. If they're in the same sign, it's a speed up function. So the rule is then, to talk about what happens to the linear slope per year of age, we take the quadratic and do what to it? Cut it in half or multiply it by 2? Cough, cough, homework question. In both classes, actually.
Multiply it by 2 because of your derivative, sorry.
Yes, multiply by 2. This quadratic slope is half the rate of acceleration of the function. To make it the full rate and talk about how the linear slope changes per year of age, then we multiply it by 2. let's do it again. Grip strength. So same deal. We have a quantitative predictor that had a linear relationship with cognition. Let's see if it needs to be a different kind, nonlinear. Grip strength is centered at 9 pounds per square inch. This is Stata output, or nope, this is R output instead. Back up a little bit. What's my R square for this model? Where do I look for that?
The PRE.
Yep. Notice that I stopped bolding things? Because I'm taking the training wheels off. That's what's happening here. Because the output is not going to show you like what matters, right? If it did, I would have no job. So yes, this thing. So this is proportion reduction and error. If you don't use my summary functions, it shows up at the bottom of the LM output. So, and it's labeled as such. So this is the R square for the model. Yep. And let's see here. The same questions as before. So the R square from the Pearson correlation was 0.0585. R square is now 0.0588. So another change in the 4th decimal place. Is that increase significant?
According to your output, yes.
Stupid scientific notation. This threw me off. I was like, yeah, that
Oh,
looks
wait.
small.
That's
Nope.
But that's 0.67, never mind.
Yeah,
That-
that's
or-
0.6. Yeah, so e to the negative 01 means move it over one spot.
Could you scroll to the right? I know you I think you have your 7 and your 1 switched in your P.
Oh, so, yeah, I did. Thank you.
No problem. I
No,
have
I
typos
appreciate
all over my
these-
stuff too.
Yeah,
so.
no, and if you're teaching, by the way, fix your errors as soon as someone points them out, or like that day.
Otherwise, you'll forget.
That's right. 2 years from now, when I teach this again or whatever, I'll be like, nope, I have no memory of this.
So I do have a question before we go forward.
Yes.
So when we found out on the previous one that the squared term was not significant,
Mm-hmm.
we need to make sure that we went to the model in which we only had the linear term for the slope of that variable. Yes?
In this case, it doesn't have to be a model. The Pearson correlation tells you the same information.
Well, but I meant if we were to make a prediction, we'd have to make sure we use the one in which we have x to the first power, not with the square.
No, both.
Okay.
So if you want to make a prediction that for the quadratic model, both the linear slope and the quadratic slope join that prediction. Because otherwise, the square term is not quadratic, it's a mix of the two.
Right. Never. I'll just.
Okay, maybe we can talk after
We'll
class.
talk after
Okay.
class. Maybe during class, maybe when we think it done.
So then this time, the intercept is 24. It's for somebody who has 9 pounds a square inch.
85.
Yep. Not age 85 anymore, because age is not in the model,
Oh, yeah.
but somebody who can squeeze 9 pounds per square inch.
Okay.
Now this pattern, what pattern is this quadratic creating when I've got a positive linear and a positive quadratic? Is this a speed up or a slow down? Speed up. More positive. So grip strength is positively related to cognition. So the stronger people are smarter. Make sure you go to the gym then, get smarter. And that is especially the case in extra strong people. The effect of grip strength is strengthened at higher levels. Yes, and I'm deliberately being funny about that because this is not causal inference. That's a different class. And this design would not have supported that anyway. Next up is dementia group. So we have our 2 predictors here. We're looking at a bivariate relationship. So you've seen an example of this before, but I thought it might be good to walk through the logic again.
So we did our subtraction and all that good stuff.
So here's my model. The 2 slopes work together to differentiate the 3 group means. Here's how they do it. So if I use the model to plug in predictions, so the mean for none would be given by this, because none is the reference group where both of these predictors are 0. So that means that the mean for none is just beta 0. If I plug in 1 for the future group, then the mean for that group is beta 0 plus beta 1. So I'd have to get that as a linear combination. And likewise, for the current group, I plug in a 1 there, and then I have beta 0 plus beta 2. That means in terms of the 3 differences, This is how the model says what the mean is for future, beta 0 plus beta 1. This is what the model says it is for none, so then the difference is just beta 1. So that's what beta 1 must mean. It's how future differs from none. None is the reference. Likewise, none versus current, same idea, ends up being just beta 2. So you don't need to write statements and ask for these. These are direct model parameters. But this one, you do. So future versus current. As a general rule in these models, any question that involves the reference group is in the model somewhere. Any question that involves differences between non-reference groups, you need to ask for as a linear combination. So how the model says what current is minus how the model says what future is gets you to this result, beta 2 minus beta 1. And so we'll have to ask for that. Okay. Any questions on that much, just the logic? So 3 fixed effects given directly, the other 3 are linear combinations, and then we'll know all 3 means and all 3 mean differences. So survey says, significant model, R squared is 0.17, so I can take the square root of that and then turn it into a correlation metric to talk about its bivariate relationship with cognition. In the results then, the constant here means what?
The no dementia?
Yeah, no dementia group. So we're not talking about age 85 or group 9 because they're not in the model. That's going to be the next model. We're getting there. What happens to the future group? The future group, lower by 5.7. Dementia is not good for you, it turns out. How about the current group?
It's even worse.
Yeah. Not lower by 16. And the difference between these looks like about 11 to me. But I don't have a standard error for it looks like about. So I need to ask for that. So then in Stata here, I have lincoms that are generating the means. So I wrote in the comments where these are coming from. So there's the 27 that's already in our output. I'm doing this for pedagogical purposes. The model implied means for the other groups then are right here. I am then asking for the remaining mean difference. Or actually, no, this is not that one. This is just the difference between none and future, because what I'm doing here is getting effect sizes. So remember, this is accessing the stored results and then doing math on them. So this part of the code you don't need to change. This, you just recycle it. You can take it and use it. So here's the result then. We have a coefficient, and here are some effect sizes you can use for it. D, as a standardized mean difference, means that people who have future dementia are lower by about 0.44 standard deviations. That tends to be more interpretable for group difference types of variables. For the difference between none and current, the 16, that has a large effect size of 0.86, so 0.86 standard deviation difference. And the one we're missing then, the difference between none and, future and current, there's the 11-ish, minus 10.7, and there's the effect sizes that go with it. So now we have all the pieces. And corresponding R code for this, I included the output as well. So same R square, 0.1763. Here's my table that gives the fixed effects that are directly in the model. And in R, it's GLHT you can use to create linear combinations. So remember what these numbers mean? Folks who are learning R? Do we want to talk about this, or you feel good with this?
I'll say I'm good. but
You
I
feeling good?
I can't speak for anyone else.
I'm good with awkward silence. I'll just wait.
Anybody else using R?
Do we want to hear about the
Besides me?
numbers? Yeah, fair. Zoomers? Zoomers have been quiet today. Well, the short answer is that these values are multipliers. So this is like a menu. Like picture yourself up at the drive-thru. Like for this one, be like, yeah, I need 1 beta 0 and I need 1 beta 1. And they're like, would you like a beta 2 with that? No, thank you. Okay, your total is $37.20 because fast food is ridiculously expensive right now. It's,
It costs more to get fast food than eat in.
yes, my mom can't believe that my niece, her granddaughter, makes $15 an hour sacking groceries. And then I point out, look, Mom, but if she wants to go get lunch, like on her work break, she has to spend $15 to get lunch. Just like I made $5 an hour and I had to pay $5 to go get lunch. Like it's the same. Money is in logits. That is a joke you will understand in the spring if you come back. All right, so then I built a function that spits out the answers and appends the confidence intervals. And then I built another function that appends all of the effect sizes. And so then you can get that for everything, even though they're not really meaningful for the intercepts. Okay, doing okay so far? So now we have answers to questions about how related things are without controlling for the other stuff. Do you think that there are relationships between age and grip strength? There's a little tiny one. We looked at the correlations for that. Do you think there's relationships between age and dementia status? Probably. To answer that question, we would have to predict age with dementia group to get that bivariate relationship. I could go through that with each of the predictors. But the point I'm trying to make is that these predictors have overlap. Most of the case, that will be true. So the question is, how do they predict the outcome uniquely, working to, when everything is in the model at the same time? So here's where we're going to end up. Okay, we're going to put in a linear effective age because we just learned that that was sufficient, a linear effective grip because that was sufficient, the binary variable for gender that we already knew about, and then we're putting in the 2 dementia variables here. Now, wouldn't it be nice if you could get all of these models with like just this and then add this and then add this and then add this in one fell swoop? Wouldn't that be nice? Watch that. One line. There is a command I just learned, actually just this year, called nestreg, which is a way of estimating nested models. Nested means one is a subset of the other. So what this does then is say, okay, start with a model with just age, then add grip, then add gender, then add dementia. And it spits out all of them. So block 1, here's the results with just age. Block 2, adding grip. Block 3, adding gender. Block 4, adding dementia group. It's glorious. I know. Oh, here's the best part. They do this little table where they organize everything for you.
They're all significant.
It is awesome. So block 1 is just age. Age had an R-square of 0.0291. Block 2 added grip strength, brought the R-square up to 0.07, so the difference is right here. And here is the F test of that difference, degrees of freedom, NF. Then block 3 added binary gender, brought the R-square up to 0.099 for a change of 0.02. And then the last one, for dementia group, brought it R-square way up to 0.7277 for a change of 0.18 or so. Yeah, the Zoomers are happy with this too. Now here's a question. Why is it that this degree of freedom is 2 and the others are all 1?
Isn't that our dementia group?
Because it's for dementia group and I have 2 new slopes in. So in each of these prior cases, the significance of the change in the R-square would be given just by the p-value for the new slope because it's the same thing. So we can actually test that. Theoretically, yeah. Yep. P-values are all 0, so that's not going to be a great demonstration. But the change in the R-square is what we're looking at. For this one, though, because there's 2, this is where we would need to ask for this separate test because you need to lump them together to get the joint contribution of the 2 slopes. So this would be, if you are interested in saying, like, first I controlled for age, here's what happened, Then I controlled for grip, and age was still significant, and grip was significant. Then I added controlled for gender. There's a fly on my screen. It's weird. It's November. They're supposed to be dead by now. Yeah. More good news. And then we added dementia. So you can sort of talk about these in layers, and that's what happened in chapter 2. So in your next homework, you can use this. And it's one line of code to do the entire homework nearly. I know, right? I like Stata because it is built for data analysis. It is not built for like coding and data management and programming kinds of things. It is built for data analysis. So they have all these little like quick ways of doing stuff. Very cool. Now for the last one, here is, I wanted to do an alternative version of a comparison. What if I wanted to know how much information the demographic variables contributed uniquely, so age and gender? Nothing in here so far would tell me that because they were entered at different points. So I need to do it a different way. What I'm going to do is say, hey, I have this new nest egg thing. I have no idea what it looks like when you store stuff out of it, but I'm going to store it. So I'm saving the results of this analysis to an object called combined. I am then saying, hey, can I see what's been stored so that I can figure out where the information is to get the effect sizes? So I skipped that printout, but this is what it would do. So I'm saving the model sums of squares and the residual sums of squares so that I can get built effect sizes below. So I'm using a statement called test to say what if age and gender were taken out of the model. There's the F test for that. And then I'm literally taking them out of the model so I can get the effect sizes that go with it. So this is what I did in example 4a. So even if you don't have the variables entered in the same step, you can still get joint contributions out of your final model with this way. In terms of effect sizes for the fixed effects, I'm using KeyCore for that. So these generate partial and semi-partial correlations in their squared versions. And then I added code to get effect sizes for the dementia and binary variables in a D metric that might be more useful than ours. Ta-da. Now R folks, sorry, you got to write more code. Or you got to find something like NestReg. Okay, Erica, I'm tasking you with this. Go Google stuff. Ask the Google if there's NestReg in R. And report back to us, please. Okay. See, I'm not of the opinion that there are no other programs open on your laptops in front of you. I'm just going to work with that assumption that there's stuff happening. She's like, I'm not multitasking.
No.
Never.
No.
Yeah, just don't leave your email open while you're in class, because then it's like the little thing's just going to pop up and like annoy you. I took off notifications of email a long time ago for that reason. So what has to happen in R is that we have to fit these models manually one at a time. So the first one we put in age, the second one we put in grip, the third one we put in gender. So here are the results from each of those. And then the last one we put in everything. So you have to build the sequence. So more code, but it's all like copy it, change one thing, copy it, change one thing. Yep, that kind of thing. However, I tried to help you by building this function to do the F tests and the effect sizes. Yeah. So then I essentially rebuilt that table with these three commands right here. So testing against the first model after adding grip, then add sex, then add dementia. And so here are all the F tests and effect sizes for all of those things. To do the same thing with respect to age and gender as demographics, I take them out of the model and then run the same function, and I can get the F and R square for those things as well. And then I built a function for effect sizes for the model implied fixed effects. Last but not least, GLHT to get future versus current. So this is beta, let's see, 1, 2, 0, 1, 2, 3, 4. Yeah, so this is beta 5 minus beta 4. That's what is happening here. When you see the numbers of subtraction, negative signs. And so I built, then that's the missing contrast, the negative 11, and then here's the effect sizes that go with that. And then we get to results. Anything yet? There might be. Okay, keep it posted. So here's the table. that I have a couple different tables in here. I want to walk you through what I looked at. Let me fix my minus signs. I'm not even following my own example. Control H, fix the dashes, put a real minus sign in there, replace all. No, I don't want to fix the rest of the document, thank you. There, it's been fixed. So note that this is a table. These are not like numbers entered as text. What I always do is build my tables in Excel because it's a lot easier to manipulate the sizes of the rows and columns, and then I just paste them in here. And if they don't paste neatly and I don't want to fight with Word, I'll paste them in as an object and deal with it later. Once your paper is accepted, the people who publish it will not allow that, but the reviewers will be fine with it along the way. So this is a standard table you would see in a regression type analysis. I'm reporting the Pearson correlations that we had where it was possible, and I'm reporting descriptive statistics for each of these variables in the same table. You're allowed to do that. Then I described the separate models. So where we added quadratics, told them what happened, described the dementia bivariate model with just that in it, told them what happened, and all the patterns of differences. Then we had, then I would talk about the combined model. So here's information about that. Here is a summary table of the process. This is literally a nicer version of the data output in terms of how the stepwise analysis was conducted. And then here are the results from the final model where I have estimate, standard error. I don't need t, right? Because t is estimate divided by standard error. So they can figure that out if they want to. T isn't really helpful other than getting a p-value. So everything is significant. And then we have our effect sizes in here as well. And that's it. Save. What do you think? You feel like you can do this? Yeah, I think you can. So I have an example. Homework 5 will very closely follow this, I would say. Not exactly, but closely. But that's not ready yet, because it's not due for a while.
Should we be looking at the in-between step?
The in-between step.
Not the actual assignment, but the formative assessment.
Oh, that one, since you have homework due on Monday, I'll release it on Tuesday, and
Okay.
that'll be the next thing. So yeah,
Okay.
let's look at the syllabus real quick and make sure that I'm not speaking out of turn, because sometimes I get confused as to what class I'm talking to and what that means.
Mm-hmm.
It happens. It's especially confusing, so I think it was a year ago I was teaching 2 different classes that a lot of people were both in, and then I was like, I don't know what I'm talking about right now. Because looking out in front of me is a good clue as to which class I'm in, but not if they're the same people for the most part. Let's see, week 11 we just finished up with, my goodness. So yes, homework is due Monday, quiz after that, Thanksgiving break, quiz after that, then homework 5. So not for like a month or so. And then homework, the last homework is due Thursday of finals week. So that'll be homework 6. What are we squinting at? I can make it bigger.
Oh, okay, never mind, got it.
Yep. So we're getting
having
there.
2 formative assessments before the,
Yes.
yes.
Yeah,
before the
that's
other two.
because I did not want to be the kind of person who makes you have a homework
Thank
due
you.
right when you come back from Thanksgiving,
Thank
because that's just mean.
Thank you.
But I think a formative assessment right when you come back is a
Yeah,
reasonable thing.
That's okay.
Because, you know, it's 2 points, shouldn't take too much effort. So, all right,
Cool.
then I think I'm done. Like, I don't have anything else to say about this, and the next lecture's not ready yet. I'm just keeping it real, okay? So I can pretend to be like, oh, I think it would be nice for us to end early for a change, and the reality is I'm not ready to keep going yet. So, but I will be by Tuesday, that I promise. I think we've hit everything in here as well. Are there any questions or comments on these ideas that you want to go over again?
Need to practice.
Need to practice. Okay.
That's coming.
Yes, practice is coming. Yep. Okay. Well then, thanks for being here, everybody. Grab some candy on your way out and enjoy an extra half hour or so of your life back, or maybe 20 minutes, something
I
like
get to
that.
go car shopping.
Yes.
Oh,
We're going to go buy a bowling ball.
Yours is less expensive.
Yeah, it is.
I mean, even
All right.
even a
I
pro